Our first question is from a Prelim 2020 exam paper. So we've got question 8. Determine f prime of x from first principles if f of x is equal to negative 2x squared plus 6x. So let's start by writing out our formula. So we've got f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is our formula that we need to use whenever we calculate a derivative or f prime of x using our first principles. Now keep in mind that this formula can be located on your formula sheet if you forget it. So before we do that, I'm going to first find f of x plus h separately, and then I'm going to substitute it into my formula. So we've got f of x, which is equal to negative 2x squared plus 6x. From here, I now need to find f of x plus h. Now, wherever I have x, I'm going to replace that with bracket x plus h. So I'm going to write out my f of x, but put brackets wherever I have x. Now, in place of x, I'm going to replace it or substitute x plus h. Think of it as if you were told that x is equal to x plus h. All you need to do is substitute x plus h into that position or into that place of x. Now from here, I can directly substitute this into my formula. So we're going to bring down the limit as h approaches 0. Keep in mind that we have to continuously bring it down until we substitute h as 0. It's a reminder that h is equal to 0. Once we've substituted h is equal to 0, that is the only time that we can drop it or not bring it down. Now, keep in mind the whole goal of using your first principle is to simplify your numerator such that it can cancel out the h in your denominator. Because you cannot substitute h as 0 if you will get a 0 denominator. That is going to give you an undefined answer. So the goal of this is to simplify the numerator such that it can cancel out that denominator so that you can substitute h as 0 such that it does not give you an undefined answer. So we substitute f of x plus h. That is going to give us negative 2 into x plus h squared plus 6 into x plus h. What we've now substituted is only f of x plus h. We now need to substitute f of x. So we bring down the negative. We open up a bracket because we are substituting multiple terms. So we substitute negative 2x squared plus 6x. The reason that we put a bracket in front of our term or in front of the terms that we are substituting is because this negative is going to affect both terms. So don't forget to bring down your over h. From here, we can bring down the limit as h approaches 0, and we can now start to simplify our numerator. So I'm going to bring down negative 2, x plus h all squared becomes x squared plus 2xh plus h squared. Now we can multiply positive 6 into the bracket. Positive 6 times x which is going to give us positive 6x. Positive 6 times h, which is going to give us positive h. Next, we can multiply the negative into the bracket. So negative times negative 2x squared gives us positive 2x squared. Negative times positive 6 gives us negative 6x. That is going to be all over h. From here, we can see that positive 6x cancels out negative 6x. So let us continue to simplify this even further. So we can bring down the limit as h approaches 0. We keep bringing it down because we are not yet in a position to substitute. Now from here, we're going to multiply the negative 2 into the bracket. So that is going to give us negative 2 times x squared, resulting in negative 2x squared. Negative 2 times positive 2xh gives us negative 4xh. Negative 2 times positive h squared gives us negative 2h squared. From here, we just bring down positive 6h plus 2x squared, and that is all over h. From here, we can see that negative 2x squared cancels out positive 2x squared. Reason being is that when you add them up, they give you 0. Now we bring down the limit as h approaches 0. Now we can bring down what is left over after we've added up the like terms. Now that is going to be negative 4xh minus 2h squared plus 6h all over h. From here we can see that we have a common factor. This is when we can now start to cancel out our denominator. So we bring down the limit as h approaches 0. If we take out our common factor being h, we are then left with negative 4x minus 2h plus 6. That is all over h. And as we can see, h cancels out h. And we are then left with the limit as h approaches 0 of negative 4x plus 6 minus 2h. So from here you can see that we no longer have a denominator of h, which means that once we substitute h equals 0, we will not have a 0 denominator, which means our expression will no longer be undefined. So we can now substitute h equals 0. Now, because we are substituting h equals 0, we do not need to bring down the limit as h approaches 0. Think of it as you are now using up that limit as h approaches 0 because you are substituting it in. So because you are substituting it, you don't bring it down. You've used it already. So we have minus 4x plus 6 minus 2, and we substitute h equals 0. From here, we can now simplify this. Negative 2 times 0 is 0. So we therefore have negative 4x plus 6 as our answer. Now that is f prime of x using our first principle. We can also check our answer using our normal derivative method. So if we write down f of x, here's f of x on top. So if we were to use our normal method, so we have f of x equals negative 2x squared plus 6x. And if we find f prime of x, we say exponent times coefficient, so 2 times negative 2, that'll give us negative 4. We bring down our variable and then we subtract 1 from our exponent, leaving us with 1. Next, we multiply our exponent, so the exponent of x is 1, times the coefficient of x, which is positive 6. That gives us positive 6. From there, we subtract 1 from the exponent, so x to the power 1 minus 1 is going to give us x to the power 0. We know x to anything to the power 0 is 1, so that will be 6 times 1. 6 times 1 is 6. So that will then give us negative 4x plus 6. Let us see if we have that answer. Yes, we do. So we can now confirm that our answer is correct. Let us now move on to question 8.2. Question 8.2, evaluate dy dx if y is equal to 2x squared plus 1 over 2 x to the power 4 minus 3. So let us find dy dx. So this is question 8.2.1. So we have y equals 2x squared plus 1 over 2 x to the power 4 minus 3. Now there's a few rules that we need to remember when deriving. Those rules are, when we derive, it's always going to be the exponent times the coefficient and subtract 1 from the exponent. So if we use this as an example, let's say ax to the power n. If we want to derive ax to the power n with respect to x, that is going to be exponent, which is n, times coefficient, which is a. So that will be a times n, bring down your variable, and then subtract 1 from your exponent. So n minus 1. Now keep in mind the derivative of a constant. So let's say we have a constant negative 3. The derivative of a constant is always going to be 0. It does not matter what the constant is, whether it's negative 3, positive 3, negative 1, 10, a million. The derivative of a constant is always 0. So let us do one more example of the first rule with an actual numerical exponent and coefficient. So if we have, let's say, 2x cubed, and we need to derive this. So it's going to be exponent times coefficient, bring down your variable, and then subtract 1 from the exponent. That is then going to give you 2 times 3, which is 6, x, 3 minus 1, which gives you 2. So 2x cubed, if you were to derive that, it would then give you 6x squared. Let's include one more rule. If we derive something whereby the exponent of our variable is 1, we just drop the exponent and the variable. We only write the coefficient. So I'll do the long method so you can see why, and then I'll do the short method. So if we want to find the derivative of, let's say, 3x, our answer is going to be 3. Reason being is that, let us do the long way, we'll multiply the exponent, which is 1. Keep in mind, if your variable does not have an exponent, it's an invisible 1. If it does not have a coefficient, it's also an invisible 1. We'll do an example with that after this. So we'll multiply the exponent, which is an invisible 1, times the coefficient, which is 3. So 1 times 3. Bring down your variable and keep in mind the exponent is 1. So we subtract 1 from our exponent. Always remember that you're always going to subtract 1 from the exponent. It doesn't matter what the value of the exponent is, you always subtract 1. Whether it's 10, 1, 2, 3, 5, negative 10, always subtract 1. Now if we continue with this, we have 3 times 1, which gives us 3. We then have x to the power 1 minus 1, which gives us x to the power 0. We know that anything to the power 0 is 1. Keep in mind that this whole thing is not equal to 1. It's only the x part that is equal to 1, because it is only the x that is raised to the power of 0. If the entire thing was raised to the power 0, it would be 3x all raised to the power 0. So this now becomes 3 times 1, which therefore gives us 3. A shortcut is to always remember that whenever your variable has an exponent of 1, only write down the coefficient. Now, let us do an example with x. So if we have, or if we need to find the derivative or the first f prime x of x, we need to derive x. Keep in mind that x has an invisible 1 as an exponent and an invisible 1 as a coefficient. So we derive. Whenever we derive, it's exponent times coefficient. So 1 times 1. Bring down the variable, subtract 1 from the exponent. 1 times 1 is equal to 1. X to the power 1 minus 1 equals x to the power 0. X to the power 0 is 1, so in place of x to the power 0, we substitute 1. 1 times 1 is 1. Or shortcut method is to just write the exponent of the variable. That exponent is 1. So if you were to derive x, you'd end up with 1. So let us do a quick summary of our rules. It's always exponent times coefficient. You write that answer. You bring down your variable and you subtract 1 from the exponent. If you are deriving a constant, always remember that the derivative of a constant is 0. If you were deriving something whereby the exponent of your variable is 1, just bring down the coefficient, or the answer of that derivative is the coefficient. So let's get back to our question 8.2.1. We now need to find dy dx. Because this is in a format, or it is in an acceptable form to derive, we can straight away go and derive. We do not need to simplify or change the form any further. So we bring down, or we introduce dy dx. Keep in mind that the numerator represents the name of the equation, so that y is because our subject is y. It is stating we need to derive equation y with respect to x. So we are deriving equation y is the name of the equation, with respect to x. X is the variable that we need to concentrate on. Keep in mind that this will become important if you have multiple variables within your equation. So if we had, let's say for example, ax squared plus 1 over 2x to the power 4 minus a, and we were asked to derive or to find dy dx, that means that we need to treat a as a constant. We need to think or see a as a numerical value, because we are not deriving with respect to a. We are only deriving with respect to x. So let us proceed. Now, just as previously discussed, we are deriving equation y with respect to x. So we are going to multiply the exponent which is 2, times the coefficient, which is also 2. So 2 times 2 gives us a value of 4. Next, we bring down the variable and we then subtract 1 from the exponent. So 2 minus 1 gives us a value of 1. And we know that we don't need to write 1 in our exponent area because 1 is just invisible. You can write it if you want to, but you don't have to. Let us look at the second term. So we're going to multiply the exponent, which is 4, times the coefficient, which is positive 1 over 2. 4 times a half is just positive 2. Next, we subtract 1 from the exponent. 4 minus 1 leaves us with 3. And lastly, we know that the derivative of a constant is just 0. Now, instead of writing plus 0 or minus 0, we can just leave it out because we know that 0 is nothing. And this is our answer. The derivative or dy dx of y equals 2x squared plus 1 over 2x to the power 4 minus 3 is equal to 4x plus 2x cubed. Let us have a look at our next question, which is 8.2.2. So 8.2.2, evaluate f prime of x if f of x is equal to x cubed minus 5x squared plus 4x all over x minus 4. So if you look at that equation, you can straight away see that you are not in a position to derive as yet. You cannot derive that. Reason being is that there are multiple terms in the denominator area. If you have multiple terms in your denominator whereby one of those terms is the variable that you are deriving with respect to, you cannot straight away derive, nor can you bring that denominator to the top and change the exponent. Reason being is that there are multiple denominators. So let us write this down and then we'll have a look at it. Now, if you notice, like I mentioned earlier, we have multiple terms in our denominator, whereby one of those terms is the variable we are deriving with respect to. Now, usually if we have our variable as our denominator, let's say, for example, we have 3 over x, and we want to change this into a form that is derivable, because keep in mind, 3 over x, we cannot derive that as yet. We need to change it. So we need to bring x to the top. That'll give us 3 to the power x minus 1. Now we can derive it. The variable that we are deriving with respect to always needs to be in the numerator position. So if we look at this, we cannot bring 4 minus x to the top. If we were to bring 4 minus x into the numerator position, it would then become x minus 4 to the power negative 1. And at a grade 12 level, we've not yet learned how to derive this. In order for us to derive this, we would need to make use of our chain rule, which we did not learn in grade 12. We'll learn it next year at a university level. So we cannot use this option. And keep in mind, you cannot solely take x into the numerator position and leave behind the 4. What I mean by that is you cannot just move x to the top only and leave the 4 behind. Keep in mind that the x and the 4 are connected, they are locked together, they are joined. Think of them as one thing. If you were to move it, you'd have to move both as one thing. So we cannot do that. So what is our next option? Always remember this. Whenever you have multiple terms in your denominator area, and one of those terms is the variable that you are deriving with respect to, always remember that you now need to simplify the numerator such that it cancels out with the entire denominator, meaning that the whole of x minus 4 needs to get cancelled out. We need to simplify our numerator such that we would end up with x minus 4 in our numerator section so that we can cancel numerator and denominator and derive what we are left with, or what would be left behind. So let's see, how can we derive our numerator? So first of all, we're going to bring down f of x. We are not going to introduce f prime x as yet. Reason being that we have not yet derived. We are still simplifying. At the step whereby we derive, that is when we will introduce f prime of x. So for now, we keep it as f of x. So if you look at our numerator, how can we simplify this? First of all, you should notice that there's a common factor, that common factor being x. Look at term 1, you have x in it. Look at term 2, you have x in it. And look at term 3, you have x in it. So we take out x as a common factor, and we will be left with x squared minus 5x plus 4, and that is a trinomial. We can now simplify or factorize that trinomial. Factorize being a better word. We would not simplify, we would factorize the trinomial. Now, when we factorize that trinomial, one of those terms or one of those brackets needs to have x minus 4 in it in order to cancel out our denominator. So let us factorize x squared minus 5x plus 4. If we factorize it, we are going to end up with x minus 1, x minus 4, all over x minus 4. And as you can see, we now have something that can cancel out our denominator. So we are then left with f of x equals x into x minus 1. So we've cancelled out our denominator. We no longer have x in the denominator position. So are we in a position to derive as yet? No, we are still not in a position to derive. Reason being is that we have x times x minus 1. We need to simplify that, and then we will be in a position to derive. So let us simplify this. So if we simplify f of x, we would end up with x times x giving us x squared, x times negative 1 giving us negative x. Now we are in a position to derive. This is something that can be derived. So we introduce f prime of x. So just as we previously did, we are going to multiply the exponent, which is 2, times the coefficient, which is 1. That gives us 2. We are then going to bring down our variable and then subtract 1 from our exponent. So 2 minus 1 gives us 1. So when we derive x squared, we end up with 2x. Thereafter, we are going to try and derive the next term. So negative x. As I previously mentioned, when the variable has an exponent of 1, the easiest way or shortcut is to just bring down the coefficient. So we just bring down negative 1. That is how we derive negative x. Alternatively, if you want to take the longer approach, you can multiply 1 times negative 1, so the exponent times a coefficient giving you negative 1. You bring down x and subtract 1 from the exponent. That'll give you negative 1x to the power 0. From there, we know that x to the power 0 gives us 1, so negative 1 times 1 gives us negative 1. That is how we end up with negative 1. So Our final answer is going to be f prime of x is equal to 2x minus 1. Now that is question 8.2.2. The goal of this question was to find f prime of x given f of x. Now something important to take note of is that because we have multiple terms in our denominator and x is one of those terms, we cannot derive as yet. We first needed to simplify the numerator such that it cancels out with the denominator. Then we were able to derive. Now let's move on to question 8.3. So we have question 8.3. The tangent to the curve of y equals 2x squared minus 3x minus 5 is drawn at the point 2 and negative 3. So two important pieces of information. This curve is a parabolic function. More specifically, a positive parabolic function or an a greater than 0 parabolic function, meaning that it is going to have a smiley face shape. Next, we need to understand that there is a tangent to this parabolic function, and the tangent and the parabolic function touch at the point 2 and negative 3. Now, sentence number 2 states a straight line parallel to the tangent passes through the y-intercept of the curve is then drawn. Determine the equation of the straight line. So there's three functions in this particular question. We've got our curve, which is represented by y equals 2x squared minus 3x minus 5. We also have the tangent to that curve, and in addition to that we have a straight line that is parallel to our tangent and cuts the curve at the y-intercept, meaning that it cuts the curve at 0 and negative 5. Now we need to determine the equation of the straight line. Keep in mind we're determining the equation of the straight line that is cutting the y-intercept of our curve. We are not determining the equation of the tangent. So to make our life easier and to understand what is going on, let us represent this in a drawing. So we have question 8.3. Let us start by drawing our x and y axis and then sketching our graphs. Now keep in mind we had our parabolic function, which was y equals 2x squared minus 3x minus 5. So let us sketch this. First, we can identify that our y-intercept is at negative 5. So let's draw it over here. Then we can have our curve. That looks like this. So this is our parabolic function. This is our curve. Next, let's go back and read our question to see what other information we are given. The tangent to the curve of y equals 2x squared minus 3x minus 5 is drawn at the point 2 and negative 3. So our tangent touches our curve at 2 and negative 3. So let us make that point over here. Let us state that this is 2 and negative 3. So let us now draw that tangent, which is a straight line. So that is our tangent. Just make a tiny subscript tan to show that is our tangent. So we've now drawn our parabolic function and we have the tangent to that function. Let us go back and read our question to see what additional information is given. A straight line parallel to the tangent passes the y-intercept of the curve. So let us now draw a straight line that cuts our y-intercept and is also parallel to our tangent. So that is our straight line that is parallel to our tangent and cuts our y-intercept. So we'll call this our line. Now keep in mind they've stated that these two lines are parallel to one another. That means that they have the same gradient. Always remember that parallel lines have the same gradient. So for reference, when I'm discussing the red line, which is my tangent, I'm going to refer to it as a tangent. When I'm discussing my blue line that is parallel to my tangent, I'm going to refer to it as a line. So we can state the information that was given above. The gradient of the tangent is equal to the gradient of the line. Why? Because my tangent is parallel to the line. Now, we need to find the equation of the blue line. What do we need when finding an equation of a line? We need the gradient and we need the value of c. So this is our equation of a line. Y equals mx plus c. Now, m refers to our gradient and c refers to our y-intercept, which is when x is equal to 0. Now, if you look at our blue line, it cuts the y-intercept where the value of y is negative 5. So I'll repeat that once more. Our blue line cuts the y-intercept of the parabolic function at y equals negative 5. Keep in mind that c represents the y-intercept. So we now have the value of c. Our value of c is negative 5. Now, we have our value of c, so we've got 1 out of 2 of our requirements. So next we need to calculate the gradient of the line that cuts the y-intercept. We need to find the gradient of the blue line. Keeping in mind that we only have one coordinate of that line, which is 0 and negative 5. We don't have another coordinate, so we cannot use our normal gradient method. We now need to come up with a different method of finding the gradient of the blue line. But what do we know? We know that the tangent is parallel to the blue line, therefore the tangent will have the same gradient as the blue line. And based on what we've learned from calculus during this year, we can now calculate the gradient of the tangent to the curve. Once we calculate the gradient of the tangent to the curve, that will be the gradient of the blue line. So let us start by calculating our tangent to our blue curve. So what I'm going to do is I'm going to move this to the bottom so that we can make use of this. So if we want to calculate the tangent's gradient or the gradient of the curve at that point x equals 2, we can derive once. So that's going to be 4x minus 3. Keeping in mind that the curve and the tangent meet at the point x equals 2. So we are now going to substitute x equals 2 into our derivative in order to find the gradient of the tangent at the point x equals 2. And that gives us the gradient of our tangent as 5. Keeping in mind that the gradient of the tangent is also the gradient of the line. Why? Because as we've stated before, the tangent and the line are parallel to one another, therefore they have the same gradient. So in order for us to calculate the gradient of the blue line, we needed to calculate the gradient of the tangent because the tangent is parallel to the blue line, therefore they have the same gradient. So how do we calculate the gradient of the tangent? We know that we are able to calculate the gradient of the curve using calculus. We can derive the equation of the curve to give us the equation of the gradient, keeping in mind that the gradient of the curve is continuously changing. However, the gradient of the tangent is constant. So we were able to find the gradient of the curve at the point x equals 2. And the gradient of the curve at the point x equals 2 is the gradient of the tangent, the whole tangent, keeping in mind that a tangent is a straight line, therefore it has a constant gradient. So once we were able to find the gradient of the curve, that gave us the gradient of the tangent because they intersected or they touched at the same point, therefore they would have the same gradient at that point. So we now found the gradient of the tangent, and because we know that the gradient of the tangent is equal to the gradient of the blue line because they are parallel, we then have the gradient of the blue line. So we have both requirements. We have the value of c and we have the gradient. So let us now substitute our value of c, which is -5, and our value of m into our equation. So that is then going to be, let us just label it the line. So y of our line equals 5x minus 5. And that is our equation of our blue line. Alternatively, what we could have done if we did not identify that we had the value of c, we could have used the coordinate 0 and -5. Now, why have I chosen to use the coordinate 0 and -5? It is because that is the point that the line intersects. Keep in mind that if you do not have your value of c, you need the gradient and a coordinate that is on the line. So what coordinate or what point is known that is on our line? It is y equals -5, and because that is a y-intercept, it will be x equals 0. So we can use our gradient, which is m equals 5, and we can use our coordinate of 0 and -5. From here, we can substitute our y value, which is -5, our gradient, which is +5, and our x value, which is 0. That then gives us a c value of -5. So if you did not know your c value, you could have calculated it. From there, you can then substitute into your original equation and therefore have your equation of your line as y equals 5x and substitute the value of c that you just calculated. So either option would have been acceptable. The goal for this was to identify that we can calculate the gradient of the tangent using our derivative method. So we needed to derive and substitute the x value at that point of contact to give us the gradient of the tangent. We then needed to identify, based on the information that was given, that because the tangent is parallel to the line, they have the same gradient. In addition to that, we needed to understand that because the line, more specifically the blue line, passes through the y-intercept, that means that our c value is -5. That would then allow us to calculate the equation of that blue line. Now, from here, Let us move on to the next question, which is from the exact same paper. It is from a Prelim 2020 exam, and this is question 9.1. So, question 9.1 states determine the points on the curve y equals 4 over x, where the gradient of the tangent to the curve is negative 1. So let us see what information are we given. So we have question 9.1. First piece of information, we are told that we have the equation y equals 4 over x. And as you can see, this is a hyperbolic function. Next, we are told that the gradient of the tangent to the curve, so the gradient of the tangent is equal to negative 1. So let's read our question once more to identify what we need to do. Determine the point on the curve of y equals 4 over x, where the gradient of the tangent to the curve is negative 1. So we need to determine the point of contact between the tangent and the curve. So let us represent this as a graph. So if we have our x and our y axis, let's say we've got our curve here and here. Now we need to find the point of contact of our tangent. So because it's m equals negative 1, the line will most likely look something like this. Now it's possible for us to have multiple tangents. So we can have a point of contact over here and a point of contact over here. We need to find the coordinates of those points of contact. So we are going to use the exact same method we would normally use if we were going to find the gradient. But we'll slightly change it because we are given the gradient and we need to find the x value. So normally, if we wanted to find the gradient, we would derive our curve to find the equation of the gradient, then substitute the x value at the point of contact to find the value of our gradient. So we're going to use that approach. So first of all, we need to understand, or we need to identify that 4 over x is not a function that can be derived as yet. It is not in a form that can be derived because our variable that we need to derive with respect to is in the denominator position. We need to get that into the numerator position. So we are now going to move this to the top. Keep in mind, when we move it to the top, the exponent is going to change signs. So that is going to be 4x to the power negative 1. Always remember that whenever you move something from top to bottom or bottom to top, the value of the exponent changes. So if we had 1 over a squared and we move that to the top, it would become a to the power negative 2. If we want to move it back to the bottom, we change the sign and we make it positive. So always change the sign when moving a base and its exponent. Now that it is in a form that we can derive, let us derive this. So y prime is equal to negative 4x to the power negative 2. Keep in mind of the rules, exponent, which is negative 1, times coefficient, which is 4. That is how we ended up with negative 4. We then subtract 1 from our exponent. So negative 1 minus 1 gives us negative 2. So we've now derived. Keep in mind that this is the equation of our gradient. So we can use this equation to find the gradient at any point in our curve. If we want to find the gradient at x equals 1, x equals 2, x equals negative 2, x equals 10, we can use this equation. All we need to do is substitute the x value at that point to get the gradient at that point. Why? Because the gradient of a curve is constantly changing. It's not constant as it is with a line. So usually what we would do is substitute the x value at that point. But because we are looking for the x value at that point, we now need to substitute something else. So keep in mind we're looking for x. So we need to substitute y prime in order for us to only have one unknown. Because currently we have two. We have y prime that is unknown and we have x that is unknown. But what does y prime represent? Keep in mind that the derivative represents the gradient. So whether you write it as f prime or y prime or dy dx, it's basically a different representation of stating the gradient. So we now know that that negative 1 is our gradient. So y prime represents our gradient. So we can substitute negative 1 in place of y prime. Always remember, the equation of the derivative is your equation of the gradient. That means the subject of the derivative equation represents the gradient. So whenever you substitute an x value into your derivative equation, you are getting the gradient, meaning that y prime obtains a gradient. Y prime is the gradient. So that is why we substituted negative 1, because we were told that the gradient at that point is negative 1. Now, all we need to do from here is solve for x. So if we were to solve for x, this would then give us x squared equals positive 4. We square root both sides and we end up with x equals positive or negative 2. Always remember that the square root gives you a positive or negative value. Why? Because positive 2 squared gives you 4, and negative 2 all squared also gives you 4. That is why you end up with both positive and negative of that value. And for those of you that are confused on how we ended up with x squared equals 4 from the previous step, I will do the long method on the side. So we've got minus 1 equals minus 4x to the power negative 2. We see that we have negative on both sides, so we can cancel them out. So we have 1 equals 4. I'm going to move x to the power negative 2 to the bottom. So we change the sign, making it x squared. From here, I'm going to cross multiply. So that gives me x squared equals 4. That is all that we did. So we now know that our value of x is positive or negative 2. We now need to find the y values because the question stated that they wanted the coordinates of the point of contact, of the curve, and the tangent. Keep in mind, coordinates refer to x and y. So they say determine the points. Points is another way of stating coordinate, right? If they only wanted the x value, they would have said determine the x value of the point of contact. But they said points, so we find x and y. Now to find y, all we need to do is substitute it into the original equation. So what I'm going to do is I'm going to separate my answers and I'm going to have it as positive or negative instead of writing it in one. So we now substitute 2 into our equation. So y of positive 2 gives us 4 over 2, which is equal to positive 2. Or y of negative 2 is equal to 4 over negative 2, which gives us negative 2. Therefore, our points are 2 and 2, and negative 2 and negative 2. So these are our coordinates or our points of contact between our tangent and our curve. Now let's move on to the next question. Question 9.2. the graph of the cubic function with equation y equals x cubed plus ax squared plus bx plus c is drawn below. Something important to take note of is that the coefficient of x cubed is 1. That is 1x cubed. So the coefficient of x cubed is known, whereas the coefficient of x squared and x are unknown, and the constant c is also unknown. Now, this will become important later on when we try to find the values of a, b, and c. Now, first bullet, f of 1 equals f of 4 equals 0. Now that 1 and 4 represent the x values. Usually you'll see the function as f of x. So if they replace x with a numerical value or a variable other than x, that means that is the value of x. So our x value is 1, our second x value is 4, and those x values have a corresponding y value of 0. So the coordinate is 1 and 0 and 4 and 0. Because our y value is 0, that means those two values or those two coordinates are x-intercepts. As you can see it here, we've got one x-intercept over here and one x-intercept over here. However, what's important about the second x-intercept is that it is also a stationary point. So the coordinate 4 and 0 is an x-intercept and a stationary point, more specifically a minimum stationary point. F has a local maximum at B, so our point B is a maximum stationary point, and a local minimum at x equals 4. So we've now identified our stationary points and our x-intercepts. Keep in mind that the coordinate of B is unknown. So we have question 9.2.1. Show that A is equal to -1, B is equal to 24, and C is equal to -16. Now, there are multiple ways for us to try and find the equation of a cubic function. But for this particular case, because the x-intercepts are known, there's one of two methods that we can use. So let us investigate both methods and then we'll determine which is the best approach to take. So we have question 9.2.1. We have f of x is equal to x cubed plus ax squared plus bx plus c, whereby we need to find the values of a, b, and c, keeping in mind that the coefficient of x cubed is 1. Now, our two methods that we can make use of are y equals ax minus x1, x minus x2, and x minus x3. Now, let us call this method 1. Now, we can use method 1 when we have 3 x-intercepts, keeping in mind that x1, x2, and x3 represent x-intercepts. Now, what does A represent? A does not represent the coefficient of x squared. I know that the question has used a to represent the coefficient of x squared, but for these particular formulas, keep in mind that the coefficient of x squared and the a in these formulas are not the same. The a in the formula represents the coefficient of x cubed, not x squared. So our value of a in this particular case would be 1. So this is our first method when we have three x-intercepts. Let's draw a graph of that so we can get an idea of what we are talking about. So this will represent our x-axis and this would represent our y-axis. If we have a function such that it has three x-intercepts, we can use method 1, keeping in mind that our x-intercepts represent x1, x2, and x3. All we would do is substitute those x-intercepts into the formula. We would then, if we are not given the value of a, substitute the x and y values of a random coordinate on the curve and obtain the value of a. Once we've obtained the value of a, we can then substitute a, x1, x2, and x3 into this formula, simplify it, and obtain our equation. If we are given the value of a, as we are in this particular case, it makes life easier for us. All we need to do is substitute the value of a, which in this case would be 1, substitute our x1, x2, and x3 values, and then simplify the equation, and we would be done. But if you notice, or if you remember, we do not have three x-intercepts. We have two only. So let us go back to our function so you can see. We don't have three x-intercepts. We only have two, that being x equals 1 and x equals 4. So let us see what method we can make use of whereby we only deal with two x-intercepts. Now I'm going to call that method 2. Now method 2 has a similar formula to method 1. We've got y equals a into x minus x1, x minus x2, whereby the value of a is still the coefficient of x cubed. It has not changed. Now, something important. In method 1, it does not matter which you label as x1, x2, or x3. As long as you substitute x-intercepts in x1, 2, and 3, it doesn't matter in which order. However, in method 2, the order matters. So, what is important about our order? It is that x2 represents the turning point and the x-intercept. Now, something important is that this needs to be squared. Why? Because it represents two things, the turning point and the x-intercept. So our second formula is a, which is the coefficient of x cubed, times x minus x1, x minus x2, whereby x2 represents the turning point and the x-intercept. So let us sketch that. So if we were to sketch this, let us actually make our sketch similar to the question sketch. So this is our value of B, which is another turning point. This is our x equals 1, and this is our x equals 4. So this would now be our x1, And this would be our x2 value. Why? Because x equals 4 represents the turning point and the x-intercept. Always remember that. So we are going to use method 2. So step number 1, we write down our equation. Y equals a into x minus x1, x minus x2 squared. Next, we substitute, whereby a represents the coefficient of x cubed. If we go back to our function, the coefficient of x cubed is positive 1. So we substitute that. Open a bracket, x minus. Now, our value of x1, keep in mind when we are using this method, x1 represents the x-intercept only, not the x-intercept that is also a stationary point. It's the x-intercept only, which has an x value of positive 1. So we substitute 1 in place of x1. Open up another bracket, x minus, now value of x2. x2 represents the x-intercept that is also a stationary point or a turning point. So that is going to be x equals 4. So we substitute 4 and don't forget to square. From here, all we now need to do is expand. So we have x minus 1 into, now if we expand x minus 4 all squared, we get x squared minus 8x plus 16. From here, we can multiply this x into the second bracket, which then gives us y equals x times x squared gives us x cubed, x times negative 8x gives us negative 8x squared, and x times positive 16 gives us positive 16x. Next, we can multiply negative 1 into the second bracket. So that would then give us negative 1 times x squared, giving us negative x squared. Negative 1 times negative 8x gives us positive 8x. And negative 1 times positive 16 gives us negative 16. From here, we can add up our like terms. So we have f of x is equal to x cubed minus 9x squared, because negative 8x squared and negative 1x squared gives us negative 9x squared. Then we have positive 16x and positive 8x, giving us positive 24x. And lastly, our constant, which is negative 16. And that is our equation of f. So let us go back to the question and see if we have the correct equation. Keep in mind, we need to have a equals negative 9, b equals 24, and c equals negative 16. So this is our value of a, b, and c. Let us go and see. And yes, as you can see from the question, A is negative 9, B is 24, and C is negative 16. So that is question 9.2.1. Next, we have question 9.2.2. Question 9.2.2 states, calculate the coordinates of B. Now, if we look at B, what is special about B, or what point is B? We can see that the coordinate B is a maximum or a stationary point. Now, if we want to find a stationary point in a cubic function, all we need to do is derive and then equate to 0 and then solve for x. That is how we get the x value. From there, we just substitute x into the original function to get y. So let's do this. We need to find the stationary point b. Our function is f of x equals x cubed minus 9x squared plus 24x minus 16. So as I've mentioned earlier, step 1 is to derive. So that becomes 3x squared minus 18x plus 24. That is the first derivative of x. Next, we need to equate to 0. But why do we equate to 0? The reason being is that the gradient at the stationary point is 0. So let's do a quick sketch so we can understand why. So if we have a tangent that touches the stationary point, we know that the gradient of a horizontal line is 0. Always remember that. The gradient of a horizontal line is 0. And that means that the gradient of the curve or of the cubic function at that stationary point would be 0. Something else to take note of is that f prime represents the gradient. So keep that in mind. So we are basically substituting f prime of x, which is the gradient, as 0 because the gradient at the stationary point is 0. So we now have 3x squared minus 18x plus 24 equals 0. From here, we can see that we have a common factor of 3. So I'm going to divide by 3 on both sides. That gives me x squared minus 6x plus 8 equals 0. From here, I can factorize, which then gives me x minus 4, x minus 2 equals 0. From here, I can finally have my values of x as x equals positive 4 or x equals positive 2. Now we can go and substitute these x values into the original function to get our y values. So f of 4, which is our y value, is then equal to 0. And f of 2 is then equal to positive 4. Now, let us go back to our question. Question states calculate the coordinate of B. So we found two coordinates. The two coordinates that we found were 2 and 4 and 0. As you can see, the coordinate of 4 and 0 is this x-intercept slash stationary point that I've circled. So that is not the coordinate of B. Next, let's have a look at B itself. As you can see, B is in the positive x and positive y area. So this is now our coordinate of B. So let us conclude. So we can now state, therefore, the coordinate of B is 2 and 4. That is our coordinate of B. So to repeat once more, how do we find a stationary point? We do that by deriving the equation once, equating it to 0, then solving for x. That gives us the x values of the stationary point. From there, we can take the x values and substitute it back into the original function. being this one. That will give us the y value. If we were to substitute it into the derivative, that would give us the gradient at those points. So if we substituted 4 into the derivative, it would give us the gradient at x equals 4. Or if we substituted 2, it would give us the gradient at x equals 2. It would not give us the y values. So be careful with that. If you want to find the y value of your stationary point, substitute it into the original function. Now let's have a look at our next question. So question 9.2.3, determine the values of k for which f of x is equal to k has only negative roots. So before we start with that question, let's write out the equation f of x equals k and try to simplify it so we can see what we are dealing with. So we've got 9.2.3, we've got f of x equals k. If we substitute in place of f of x, we have x cubed minus 9x squared plus 24x minus 16 equals k. Let us move k to the other side. So we have x cubed minus 9x squared plus 24x minus 16 minus k equals 0. So now that we've simplified the equation f of x equals k, let us go back and see what the question wanted. So our question 9.2.3, determine the values of k for which f of x equals k has only negative roots. So when they refer to roots, think of x-intercepts. So we need to find out where will this function cut the x-axis in the negative area. So as you can see right now, it's got positive roots only. It's only cutting the x-axis in the positive area. We need our function to cut the x-axis in the negative area, to have negative roots only. So let us go back to our function and see what does k represent. So we can see how best to manipulate our function. So as you can see, k represents the constant. It's not the whole constant, but it forms part of the constant. If we were to substitute a numerical value into that k, we would end up with a different constant. Right now, our constant was negative 16. If we were to substitute k equals, let's say, 1, we will not have negative 16. We'll end up with a different value. So as we can see, k forms part of our constant. Another way of thinking about it is that k forms part of your y-intercept. Because remember, your constant is where it cuts the y-intercept. And what do we associate with our y-intercept? We associate a vertical shift. So we now know that k is associated with a vertical shift. So how can we shift this graph vertically such that it only cuts the negative x-axis? So let's have a look. If we were to shift this graph down, so we lower the graph, we're now going to shift it down. This would be our new graph. As you can see, the red graph is lower than the black one. So that means we've shifted it down. You can still see that now it's become worst. Previously we had 2 positive roots. Now we have 3. So it's gotten worse. Keep in mind we need negative, not positive roots. So we can now see that shifting down is not the way to go. So let us try to shift upwards. So if we were to shift our graph upwards, You can see that it's still in the positive area, but it's gotten slightly better. We now have only one positive root. So it's improved from having two, we now have one. So let us continue to shift this graph up. As you can see, the more that we shift this graph, it's going to move into the negative area. So we've now identified that shifting our graph upwards moves it into the negative root area. So let's have a look at how we can now manipulate that knowledge, because we now know where we need to go. We need to go up in order to get negative roots. So let's see. If we have negative roots, it means our graph needs to be within this area. It needs to go left once we reach this point. Because if we were to go right, we would have positive roots. So let's use that as our anchor point, as our explanation. So I'm going to shift my graph up such that my new y-intercept is cutting the origin. So I'm now going to shift my graph like this. This is now my new graph. I'm going to use that to try and investigate what my values of k are supposed to be. So as you can see, because I need to get negative roots, I've now positioned my graph in a place whereby it's neither negative nor positive. So let's see. To the left, we end up with negative roots. To the right, we end up with positive roots. If we look at our question, they want negative only. So we now know that we need to look at the left side. So previously, our graph was cutting negative 16. That was the old y-intercept. Now I've shifted my graph up such that it is about the origin, because that is the point whereby it starts to go into the negative root area. It's not reached it as yet. At 0, it's neutral. It's not reached negative as yet. If I were to shift my graph up any further, if I were to increase my value of k any further, it's then going to move into the negative root area. So let us go back to our function and see how do we get that to become 0, because that is now our anchor point. That's what we want, because we need negative roots. So I'm going to use this as the bridge between, or an anchor point, to say, okay, I'm now in a point of neutrality, in a neutral place. If I take a step left, I'm negative. If I take a step right, I'm positive. So I'm in a neutral space. That's where I want to be. So let's find out, how do we get this to be equal to 0? So we need negative 16 minus k to be equal to 0. Because remember, I want my constant, or I want my y-intercept to be 0. So I want to shift my graph up such that it becomes x cubed minus 9x squared plus 24x plus 0. So let's simplify this equation. So we now know that our value of x is going to be negative 16. So if we substituted negative 16 back into this function, we'd have x cubed minus 9x squared plus 24x minus 16 minus negative 16. So we've now substituted negative 16 in place of k. This would then become a minus 16 plus 16, which cancels out, leaving us with 0 in this area. So we now know our value of k needs to be 16. So we now need to identify whether it's going to be k less than 16 or k greater than 16. So let's have our options. We need to identify if it's going to be k less than negative 16 or k greater than negative 16. Which one is it going to be? So let's have a look at our graph. As we can see from our graph, we need to move left to be in the negative roots. So we are going to use the same arrowhead, k less than negative 16. So we've shifted our graph 16 units up to get to this point in order for us to start having negative roots. So once we go less than negative 16, or once our k value is less than negative 16, our graph will start having negative roots. So here's an example. If we were to sketch when our graph is going to be k less than negative 16, this is how it would look. As you can see, there's negative roots. So let us go and write down our answer. Our answer of k is going to be k less than negative 16. Alternatively, you can write it as k, an element from negative infinity to negative 16. Now, this method would only apply if you want to have positive or negative roots only. So if your question states what values of k will result in positive or negative roots only, I recommend getting your graph to a place whereby it's 0. So shift your graph up or down depending on the graph you have, such that your graph cuts the origin. From there, if you want to have positive only, you'd move to the right. If you want to have negative only, you'd move to the left. That is if you have positive only or negative only as the solution. However, if your graph is specific, or if your question is specific and they state that they only want to have one root or two roots or three roots, that is when you would change your approach. So let's say, for example, this question stated they want to have one positive root. As you can see right now, there are two positive roots. But if our imaginary question stated they want one positive root only, meaning we would use k to shift our graph up. As you can see, once you start to shift upwards, it now only has one positive root, but to a certain point. Because remember, as you shift upwards, eventually it's going to become negative. And our imaginary question was one positive root only. So keep that in mind. There's a restriction. So, however, the question restricts you, what I would recommend is just drawing little sketches on your question paper to see, sketch it or shift it up to see, okay, how far can I shift up? Or sketch it and shift it down to see how far can I do it. It makes understanding it easier. So a few questions that you could get relating to K is only negative roots, only positive roots, or two positive roots, two negative roots, one positive root, one negative root, or three positive roots or three negative roots. Those are the type of questions that you could end up with. So you can refer to your textbook. There's a whole section relating to your value of k and how it affects your graph, and that should assist you. Now let us move on to question 9.2.4. Determine the values of x for which f is concave up. So let's have a look at what does concave up or concave down mean. So if we have this function that looks like this, if we were to cut this function in half, you can see that the left hand side looks like a sad face, whereas the right hand side looks like a happy face. So from here, let us break that up. So we've got this sad face side, and we've got the right hand side, which is like a smiley face. So concave down is the sad face. Think of it as to be down is to be sad, and to be up is to be happy. So concave up is the smiley face. So our question was which values of x, or for what values of x is the function concave up. So we've now identified that concave up is the smiley face area. That means we are referring to all of these x values. But starting from where? Always remember that whenever they use the word concave, always think of your point of inflection. So as soon as you hear the word concave, whether it's concave up or concave down, it doesn't matter. Automatically think of your point of inflection. Why? Because the point of inflection is neither concave up nor concave down. From the left or from the right is where it starts to become concave up or concave down. So from the right of our point of inflection is concave up. And from the left of our point of inflection is concave down. So from your point of inflection moving to the right is concave up. From your point of inflection moving left is concave down. Now we need to find this point of inflection. What is the x value of that point of inflection? Now, how do we find a point of inflection? We derive twice, equate to 0, and solve for x. It's a similar process to finding our stationary point. So let's try that out. So our function is f of x equals x cubed minus 9x squared plus 24x minus 16. So we derive the first time and we end up with 3x squared minus 18x plus 24. Keep in mind what I said earlier, point of inflection uses your second derivative. Stationary point is derived once, point of inflection is derived twice. So you derive twice and then you equate it to 0. So if we derive the second time, we'd end up with 6x minus 18. Now you equate it to 0. So you have 6x minus 18 equals 0. Now we solve for x. So that will give us 6x equals 18. Therefore, x is equal to 3. So our point of inflection is x equals 3. That is our point of inflection. Now, there's another way of calculating your point of inflection. If you do not have your function, or if you do not have your equation, you can calculate the point of inflection using your turning points. So let us go back to our graph and see what our turning points were. So our turning point is 4, that's the minimum. And our maximum is B, which if I recall correctly, it had coordinates 2 and 4. So our maximum has x equals 2, and our minimum has x equals 4. Now we can calculate the point of inflection using these stationary points. Always remember that the point of inflection is the midpoint of your stationary points. Now, this applies to the x value. If you are calculating the x value of your point of inflection, it is the midpoint of your stationary points. So let's attempt to calculate it using our midpoint formula. So x equals the maximum plus the minimum all over 2. This is our formula to calculate our point of inflection using our stationary points. So we substitute our maximum, which is 2, plus our minimum, which is 4, all over 2. Now 2 plus 4 is 6 over 2. 6 over 2 gives us 3. So it does not matter which formula you use, you will still end up with the same thing. So I'll repeat it once more. If you do not have the equation of your function and you have both stationary points, if the function has two stationary points, you can use your midpoint formula. So to find your point of inflection, you will add up your maximum plus your minimum and divide by 2. That will give you your point of inflection. If you don't want to use that approach, you can use your derivative approach. So to find your point of inflection, you will derive twice. So you'll find f prime of x and then f second prime of x. Once you find your second derivative, you then equate it to 0 and then solve for x. That will give you your x value of your point of inflection. Now that we know the point of inflection, the x value of our point of inflection, keep in mind that our original question was what values of x result in this function being concave up. So we've identified that our point of inflection is x equals 3. Now we need to identify, is it to the right of x equals 3 or to the left? So as we've previously discussed, to the right of x equals 3 is concave up, which is what we want. So what we are now going to do is we're going to follow this arrow. As you can see, the arrow is pointing right. So our answer is therefore going to be x greater than 3. And that is it. Do not put equals to, because at your point of inflection, the graph is neither concave up nor is it concave down. So it's a point of neutrality. It's not concave up, it's not concave down. So don't put equals to. It's either to the right or to the left of your point of inflection. Now, alternatively, you can represent this answer as x, an element from 3 until positive infinity. So our function is concave up for all the values of x greater than 3. And if the question was for which values is this graph concave down, it would be x less than 3.